Hey everybody, we made it through a unit and ready to start another. I kind of like this unit. I hope you enjoy it as well. It is called Logical Reasoning and Set Theory. Um, just a little bit about the unit. It's really about trying to organize information in order to make a logical decision. So lots of what we do, in fact, most of what we do in this unit will be working with Venn diagrams, just that organizing of information and being able to make a decision based on a Venn diagram. Today, though, just like every unit, we have to start off by learning some new terminology, some notation, some symbols. And so it will be a little dry today, but once we've learned this new language, we'll be able to use that language and get through the rest of the unit with no problem. You'll notice that we're starting on lesson 2. I have purposely omitted lesson 1. And this unit will be working right out of your workbook. So in order to take notes, you'll just do it right in your workbook. So I will need you to turn to page 9 and we'll go through lesson 2 in this unit together. It does have a little note here about what happened in lesson 1, the one that we're not doing. It's a little bit about how these words, and, or not, are used in mathematics. And certainly you could take a look at it. It would be helpful, but I don't know that it's really necessary. All right, so first thing that we're going to do to get started here is just to get familiar with a little bit of terminology. So there's this section called sets and set notation. I want you to read that section right until you get to example 1. So hit pause, read away, and then come on back and we'll take a look at some together. So some of the things that you've read that I really want to sort of highlight is the fact that there's a very specific way to write sets of numbers or sets of any element. Could be sets of animals, sets of fruit, sets of colors. We'll always use a capital letter and we must always use curly brackets. So it isn't just to be fancy, but it actually has meaning and we must do it that way. Important to know that word element. If I was talking about a group of students and you were in the group, you would be one of the elements of the group. And then looking at the 3 general ways of defining the contents of a set. We can list the elements. We can describe the elements with words, or we can use set builder notation, which you're already familiar with. Set builder notation is the same way that we do domain and range. And then another one I want to point out, because it's very easy to kind of miss. You really have to watch for it. That capital letter A means we're talking about a set, and the name of the set is A. And that lowercase n in front of it is referring to the number of elements in set A. And then we've got another symbol down here that we need to understand. This one is telling us that that 2 is an element of set A, so 2 belongs to set A. And this statement is telling us that 8 is not an element of set A. All right, let's give example 1 a go. Consider the following two sets. So set P, whole numbers less than or equal to 3, even whole numbers less than 10 for set Q. Pardon me. So the first thing in part A, it says list the elements of each set. Now, you will see questions where it does not ask you to do this, but it is always helpful to do this. So even if it doesn't ask you to, I think this is always your first step, is to make that list. So let's look at P. So P is talking about whole numbers. So whole numbers, let's just review. Whole numbers, the lowest whole number is 0, then 1, then 2, and so forth. So no negative numbers belong in the set of whole numbers or fractions or decimals. This list goes forever and it starts at 0. Now for set P, so capital P, curly brackets, we want whole numbers less than or equal to 3. So set P would include 0, 1, 2, 3. And set Q, capital Q, curly brackets, even whole numbers less than 10. So even whole numbers. Let's see, 0 is considered to be an even number. 2, 4, 6, 8. And we would not include 10 because it says less than 10. So those are the two sets that we're working with. In B, complete the following. Again, this is that little one that I said, very easy to miss, that little lowercase n right here and right here. Here we're being asked for the number of elements in set P. So I head over to set P and I count. There's 1, 2, 3, 4. And for part 2, the number of elements in set Q, 1, 2, 3, 4, 5. And then it says, write set P using set builder notation. So you can really use any variable you want. Now this is the one that's like domain and range. So you can use any variable that you want. I'm going to use X. And I'll say, so I'm looking at the numbers that we've got right here. And I want to describe that with an inequality sign. So X is representing those 4 numbers. So you have to think about, what do they all have in common? Well, they are all less than or equal to 3. And you have to say what type of numbers, because P does not include any decimals, any fractions. So we have to include that X is an element of whole numbers. So what our symbols are saying here is that P includes all the whole numbers that are less than or equal to 3. So if you take a look at what we have so far, when it comes to set P, up at the very beginning, they've described set P using words. And in part A, we described set P by listing the elements. And then in C, we described set P using set builder notation. So if you recall from above, that's the 3 different ways to describe a set. And then in D, which of the following is set builder notation that describes set Q? So remember, we are looking at set Q. So we want to use set builder notation in order to describe the even whole numbers less than 10. And I'll tell you what, guys, this one can be a little tricky, but you'll be glad to know that we don't have to deal with it too much. So let's start by A. We're going to use process of elimination here. So A says that Q is X, such that X is less than 10, and X is an element of whole numbers. So what this one is saying is that it's all whole numbers less than 10, so we can rule that one out because we only want the even whole numbers less than 10. Okay, let's take a look at B. Now this one's a little complicated because there's two variables in it, but I'll show you what that means. Let's just take it down here and try to figure this one out. So right in this part right here, we can figure out what X is. So X is bigger than or equal to 0, but less than 10. So X would be these numbers, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, not 10. And now let's look at E. So right here, it says E is equal to 2 times X. So I'm going to take each one of these X's and multiply by 2, and that would give me the possible E's. So 2 times 0, 0. 2 times 1, 2. 2 times 2 is 4. 2 times 3 is 6. 2 times 4 is 8. 2 times 5 is 10. 2 times 6 is 12. Now, I would go all the way to 2 times 9, which would be 18. So let's go back to what it says here at B. Set Q is equal to E, and here's the E's that we figured out. So some of these numbers are not in set Q, so this B can be ruled out as well. It does not describe set Q. All right, moving on to C. So again, start with your X's, because once you figure out what X is, then you can figure out what E is, and set Q is being defined by E. So we have to figure out what E is, but we got to figure out the X first. So if you want to give this one a try, go ahead and hit pause and see if you can figure this one out. So X, looking right here, it's bigger than or equal to 0, but less than or equal to 4. So 0 would be included. 1, 2, 3, and 4. All right, so now we're going to go on and look at E. E is equal to 2 times X. So we take every one of these X's and multiply by 2. So here's all the E's. And if I compare that up at the top to set Q, 0, 2, 4, 6, 8, I see that's exactly what I have here. So C is the proper way to use set builder notation in order to describe the numbers that we see in set Q up here. So pretty tricky with that whole combination of X's and E's, but like I said, you won't have to do too much of that. Okay, so here's where we're going to get into a bunch of symbols, and it's important that we understand what these symbols mean. So as we go through, there's quite a few here to remember, and most of these are on your formula sheet. So it might be a good idea to get your formula sheet out so that you kind of have one place to look to see all the different symbols. And you might even want to add some of your own definitions to the symbols on your formula sheet. All right, so We've got Betty is defining sets using non-negative single-digit numbers. From the list of non-negative single-digit numbers, she defined the following sets. So again, what I said earlier was it's always a good idea to actually write out that set. So they've described right here, they've described the set with words, but much more helpful if we actually write out the list. So non-negative single-digit numbers. Let's write out the elements in that set. So that would include 0. So remember, non-negative is just a way of saying positive single-digit numbers. So 0, 1, 2, 3, and we would keep on going right to 9, but that would be it. All right, so now they've broken up into other sets. So taking the list of numbers that we have here and making some smaller sets from it. So we've got set E, which would be even numbers. And over here, we will make a list of those. We've got set L, whole numbers less than 7. And we're going to make a list. And then we've got set O, odd numbers less than 7. Now remember that when we're doing this, we are only using the numbers from Betty's list. All right, so for the even numbers, 0, 2, 4, 6, 8. Now you'll notice here that 0 is considered an even number, and it's also considered a positive number. And then for set L, whole numbers less than 7, that'd be 0, 1, 2, 3, 4, 5, and 6. And then set O is odd numbers less than 7. So that would be 1, 3, 5. All right, so we can check off the first one, list the elements of each set in the space above. Now, as we go through and learn about universal set, subset, and all these new terms, we'll be looking back at the sets that we have just written here. So all the way through, we're going to use these sets and see how they're related to figure out some new terminology. So for universal set, within the context of any problem in set theory, there generally is some largest set that we have in mind. We refer to this set as the universal set. It is a set that contains all of the elements under consideration and relevant to the problem. So probably a good idea if we underlined contains all of the elements under consideration. Okay, and we'll always use a capital U for the universal set. So let's do for Betty's numbers, the universal set includes every number that would be considered. So it's actually the ones that we wrote right here. Those are all the numbers that she is considering. When we look at all the other sets, the elements in all of these sets are all included in this one. So that makes this one the universal set. So 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9 for the universal set. Okay, subset. A subset of a set is a set that contains some or all or possibly none of the elements from a previously defined set. All sets we deal with in a problem must be subsets of the universal set, and every set is a subset of itself. So that's kind of a weird little rule, but it's a good one. It comes in handy a little bit later on. Every set is a subset of itself. In set notation, this symbol is used to represent this relationship between sets. For example, set E is a subset of set U, since all the elements in the set E are also in set U. This is denoted by E is a subset of U. In set E, is set E a subset of L? If so, write this relationship using the symbol for subset. If not, write this relationship using the symbol for not a subset. All right, so let's go back. Is set E a subset of L? So if all of the numbers that are in E are also in L, then we can say E is a subset of L. So the 0's there, the 2 is in there, the 4 is in there, the 6 is in there, but the 8 is not in there. So E is not a subset of L. And the way that we write that with symbols looks like this. E is not a subset of L. Set O is a subset of set L, which is a subset of set U. Write this relationship using appropriate symbols. So set O is a subset of L, which is a subset of U. Okay, empty set to me is another one that is a little bit hard to understand because you feel like if it's empty, there's really not a set there. But in math, it is possible to have an empty set. The empty set is a set that contains no elements. The empty set is a subset of every set. Again, I think that one you should highlight or circle because later on in your questions, you'll want to come back and find that one easily. The notation for the empty set is given with this circle and a line through it. But also, if we're looking at other textbooks and older notation, we might even see curly brackets with nothing inside. All right, so here's an example. The set of all odd numbers in set E is the empty set because there are no odd numbers in set E. Provide another example of a set that is empty. So let's look up at the sets that we're already working with. Okay, so these ones, again, a little bit tricky, but everybody take a look at set O. If I told you guys I want you to pull out all the even numbers out of set O, you would say to me, well, that's impossible. There are no even numbers in set O, so that would be the empty set. Okay, that's a pretty obvious one. I think it's a good one for our examples. So another set that is empty, the set of even numbers from set O. Complement of a set, much more important, and we'll see it much more frequently compared to the empty set. The complement of set A is the set of all elements in the universal set that are not in set A. In fact, when you see the word complement, or even the symbol, this is the symbol for complement here, I want you to think of the word not. So the complement of set A is denoted by A with a little apostrophe mark. And it says write the complement of set E using the appropriate notation. So here's the right notation. Now remember, to find the complement, what we do is we look at our universal set. So I'm looking right here at our universal set, and I'm going to find the complement of E. So E is the list of even numbers. So the complement of E would be the numbers that are not even. Okay, so looking at the universal set, we're going to pull out the numbers that are not even, or in other words, they are not in set E. So that would be 1, 3, 5, 7, and 9. If we were to do this with words, the complement of E would be not even numbers. In other words, we would be looking at odd numbers. Okay, example 2. Now here, guys, we're going to have to write a lot of numbers. So you're going to have to write very small. Just a heads up on this one. There's not a lot of space here. So we are considering the following 2 sets. We've got set A, natural numbers less than 20 that are divisible by 3. So our very first job here, we should make sure we know what natural numbers are. Natural numbers are the numbers that you naturally learned when you were little. When you were counting things, it started at 1, and then 2, 3, 4. When you were counting your Cheerios at your high chair and there was a broken one, you didn't count it as a half. You just said 1, 2, 3. And you didn't have fractions, you didn't have negatives, and you don't have zeros. So natural numbers do not include negatives or zero, fractions or decimals. All right, B is natural numbers less than 20 that are divisible by 5. Okay, so question A. Explain why the set of natural numbers less than 20 is a suitable universal set. So remember, the universal set includes all the elements that are being considered. So we'll say because it includes both set A and set B. List the elements of the following sets. So set A, natural numbers less than 20 divisible by 3. So that's 3, 6, 9, 12, 15, 18. And B, natural numbers less than 20 that are divisible by 5 would be 5, 10, and 15. Now, part 3 is asking for the complement of A. So remember, complement means not. So I look at my universal set. Maybe not even a bad idea to write down the universal set. So in part A, we said natural numbers less than 20 would be the universal set. So 1, 2, 3, and up to 19. So I'm going to look at that universal set. Anytime I need to find the complement, I always go back to the universal set. I'm going to pull out all the numbers out of the universal set that are not in set A. So it would not include 3, 6, 9, 12, 15, and 18, but it would include all the other numbers from the universal set. So it would include 1, 2, not 3, 4, 5, not 6, 7, 8, not 9, 10, 11, not 12, 13, 14, not 15, 16, 17, not 18, 19, and that's it. So if I was to describe that set that we just wrote down with words, I would say that that's natural numbers less than 20 that are not divisible by 3. So if we look back up at the top here where we have set A, if I want to figure out what the complement would be, all I have to do is stick the word not in there. Natural numbers less than 20 that are not divisible by 3, and that would give me the complement of A. And then C, write a description of the elements of the complement of set B in words. So all we have to do, remember, is when we're looking at the complement of B in words, we have to get the word not in there. But it has to go in the right spot. So let's look back at the top here. So B, we're looking at natural numbers less than 20 that are divisible by 5. We just have to figure out where are we going to put the word not. So natural numbers less than 20 that are not divisible by 5. Using the proper notation, I've got B with a little apostrophe for complement of B. Natural numbers less than 20 that are not divisible by 5. And then D, this is our last example for the day. We've been introduced to a new set. We've got set C, natural numbers less than 20 that are multiples of 6. So you notice it didn't say to make a list of these numbers, but I would think that it probably makes it easier if we do actually see these numbers. So let's go off on the side here. We're going to put C. So natural numbers less than 20 that are multiples of 6. So that would include 6, 12, and 18. All right, so let's see what our questions are here. For number 1, state whether the following are true or false. So the first one that we're looking at, C is a subset of A. So we have to look and see 6, 12, and 18 from over here. There's set C. If all of these numbers are in set A, then C is a subset of A. So looking up here, I see the 6, the 12, and the 18. So this first statement is true. C is a subset of A. Okay, and then part 2, C is not a subset of B. So let's compare C and B. So looking here at C, 6, 12, and 18, comparing that to B, 5, 10, and 15. So all of the numbers in C are not in B. So C is not a subset of B, which is what this statement says. So this is a true statement. And then part 3, the complement of A is a subset of the complement of C. So complement of A we have right up here. So if all of these numbers belong to the complement of C, then this would be a true statement. So it'll be easiest if we actually have the complement of C written down. So complement of C I go to the universal set and I pick out all the numbers except 6, 12, and 18. So I'm looking back at the universal set right up here, picking out all the numbers that are not in C. So that would include 1, 2, 3, 4, 5, 7, 8, 9, 10, 11, 13, 14, 15, 16, 17, 19. So if you thought about the complement of C in words, it would be natural numbers less than 20 that are not multiples of 6. All right, so let's compare now. Here's the question. The complement of A is a subset of C. So let's look. If all of these numbers are also here, then we are going to say true. So 1 is in there, 2 is there, 4 is there, 5 is in there, 7, 8, 10 is in there, 11's in there, 13 is there, 14 is there, 16 is there, 17 is there, 19 is there. So we have a true statement. So you notice the two sets are not exactly the same, but all of the elements from this set are in this set. And that's all that statement is saying. Alrighty, so guys, we're ready for our first assignment from lesson 2. So in your workbooks, please go ahead and work on questions 1 to 7. I've got the answer key posted so that you can check your answers as you go, and we'll pick it up right here tomorrow. Have a great day, everybody.